Okay, so now that we have reviewed I and complex numbers, we're going to throw the trig back in. I love you, I'm sorry. So we're going to do trigonometric form or polar form of complex numbers. So first of all, we're going to take our regular coordinate plane, and instead of calling it the x and the y, we're going to call it the real and the imaginary. So over here, my x-axis becomes my real axis, and my y-axis is my imaginary axis. And then we can graph things like a plus bi. For example, over here they write 2 minus 3i, so that means you go over 2 in the real and go down 1, 2, 3 in the on the imaginary axis, and they get this ray. This a plus bi is called the rectangular form of the complex number. We're going to write it in some other forms in the notes. So first of all, hopefully you remember from vectors, we can add two vectors together. So I can add this green plus this yellow. So that means that my 4 gets added with my 1, which makes a 5, and my I gets added with my 3i to make a 4i. And if I go to graph this, the green one right here that's my 4i. I go 4 in the real and up 1 in the imaginary. And then for the second one, the yellow one, I go over 1 on the real and up 3 on the imaginary. And the resultant should be between them. Remember, we can use our parallelogram, and I can take this yellow one and I can slide it over right here. And then it's the same thing, just a different place in space. And then that red thing, the resultant, the 5 plus 4i, is what closes off the triangle. So let's try. Find the sum of 6 minus 2i and negative 4 minus 3i. Graph both complex numbers and their resultant. So first of all, 6 minus 2i and then negative 4 minus 3i. It's like adding with place values. It says find the sum, so I'm adding. Add the real with the real, so 6 plus negative 4 is 2. Negative 3i plus negative 2i plus negative 3 is a negative 5i. So here's my resultant right here. I'm going to graph both of them. So I'm going to graph in blue my 6 minus 2i, so that means I go over 6 and down 2 from the origin. So here is that vector. And then in red, I'll do my negative 4 minus 3i, so go over 4 and down 3. Sorry, go backwards 4, left 4. The resultant should be somewhere in the middle, but remember, we can slide this blue vector over and make a parallelogram. So as long as I start right here and my net movement is 6 in the positive, real, 1, 2, 3, 4, 5, 6, and down 1, 2. Those two blue vectors are the same thing, and my resultant would be right here, which is my over 1, 2, and my down 1, 2, 3, 1, 2, 3, 4, 5, right there. So here's my resultant. Please make sure that you can draw these and find the resultant, because it might be a test question. Okay, so the next page is where the trig comes in. So because we graph the real stuff on the x-axis, our x is going to be r cosine theta because it's real. And because we graph our imaginary stuff on the y-axis, we're going to use r sine theta for the y stuff. But the y stuff is going to end up having an I next to it because it's on my imaginary plane. We've used these formulas before. Remember that you can find r by doing x squared plus y squared. And to find the theta, remember we can do tangent of theta is y over x. So we write in polar or trigonometric form. So if it asks you for polar form, we're going to write it like this. So the r goes out front, and then it's like the r can be distributed into the ordered pair, but we write the r out front once, then it's cosine of whatever my angle was, plus I sine theta. The I is because this is the one on the imaginary axis, and this is the one that goes on the real axis. Remember, the real axis is x, and the imaginary axis is y. R is the absolute value, which is sometimes called the modulus, which is the radius it's always been, which we can find using Pythagorean theorem. So let's go ahead and try a couple. So this one says, okay, this is polar form. I want to go into rectangular form, which means I want to be in A plus BI form. So to do that, I'm going to distribute the 2 in. So I'm going to have 2 cosine 300 plus I sine 300. Please don't use a calculator. At 300 degrees, it's an ordered pair from the unit circle. You should know from the unit circle, 300 degrees. It's this one right here. The ordered pair right there is 1/2, comma, negative root 3 over 2. And then we multiply both of those by 2. So I have 2 times 1/2 plus I times 2. Hang on, that looks really bad. Let me fix that again. I, and then 2 times root 3, negative root 3 over 2. So here the 2's cancel off, so you get 1 plus the 2's cancel off here. You get negative I root 3. Technically, that's in A plus BI form. You could also write it as 1 minus I root 3. But either one of these I will accept. And these are both in rectangular form. This gray box, the one at the top of the page. This box right here is going to keep being our friend. So now we're going to convert the other way. We can use the formulas that were in this So we are going to now go from rectangular form to trigonometric form, which is also known as polar form. One thing to make sure of, just like before with vectors, please make sure you're in the right quadrant. Pretty please. So for example, this one right here, the x is negative, y is positive. This means I'm going to be in quadrant 2. Please don't let me catch you. I don't want to take points away because you just typed things in a calculator and didn't think twice about them. So this piece right here is like my x, and the 1 right here is like my y, and the I means that it's my imaginary piece. So first thing to do is I need to find r. R equals the square root of x squared plus y squared, or r squared equals x squared plus y squared. So r equals, r is always positive, so I don't need to worry about the plus and minus, negative root 3 squared plus 1 squared, square rooted. R is going to equal the square root of 3 plus 1, which is the square root of 4, which is 2. So r equals 2. Then to find my theta, I use tangent. So tangent theta equals y over x, which in our case is going to be 1 over negative root 3. That's a unit circle number. So that happens at, if you look at the first quadrant only, 1 over root 3. I know it's supposed to be negative. Just hang on a second. 1 over root 3, you would put down your index finger and flip your hand over, and your index finger is 30 degrees. It says in radians. So I want pi over 6, but I want to be in the second quadrant. So don't use that one. Theta, the pi over 16 in the second quadrant is 5 pi over 6. So then to write our answer, we would write, put the radius first, 2 parentheses, cosine of 5 pi over 6, comma, not comma, sorry, it's a plus, plus I sine of 5 pi over 6. The shorthand way to write this is the following, which is also polar form, but just a shorthand way. You write the radius, and then you write C IS, the C is for the cosine, I sine, and then because they both are always going to have the same angle, 5 pi over 6. So either one of these is acceptable. And then let me do the next one. So in this next problem, I have 0 minus 3i, where the 0 is my x and the negative 3 is my y. So if I need to find r equals the square root of 0 squared plus negative 3 squared, which is just going to be 3. And if you graph this for a second, if my x is 0 and my y is negative 3, I'm right here. I'm at 3 pi over 2. Or negative pi over 2. It says in degrees, so let's call it 270 degrees. So I know my r, I know my theta. So I can write this as 3 parentheses cosine of 270 plus I sine of 270. And then shorthand we can write 3 CIS 270 degrees. So either one of these two forms I will accept. Okay, so those ones were straightforward. They were on the unit circle. If they're on the unit circle, I don't expect you to touch a calculator. However, you should know that not all problems will be on the unit circle. So let's try the next two because they are not on the unit circle. Okay, so here's my r, and here's my theta and my theta. I need to type cosine of 125 and sine of 125 in a calculator. So I'm going to do 6 parentheses, and then I'm going to type in a calculator cosine of 125. Make sure you check your calculator that it's in degrees. And then when you do that, you should get negative 0.5735764 plus I, hang on, I'll put the I at the end. I'm going to type the sine of 125, and you should get 0.8911520443, and then the I. And then I'm going to multiply both of those by the 6. I'm going to distribute the 6 in. And so when you do that, you should get approximately negative 3.4415 plus 4.9149i. Let's try letter B. Box it in blue and do it over here. So letter B is the other way around. They gave you the x and the y, so we need to find r in that angle. So r equals the square root of x squared plus y squared. R equals the square root of 5 squared plus parentheses negative 4 squared. So r equals the square root of 25 plus 16, which is the square root of 41. I'm going to leave that alone for a second, and I'm going to go find my theta. So remember, screen, sorry. So remember, tangent of theta equals my negative 4, my y over my x. Before you type in the calculator, this is in quadrant 4 because the y is negative but the x is positive. So if you type that in a calculator, make sure you get an answer in quadrant 4. Arctan the negative 4 over 5 or negative 0.8 in the calculator, and you should get negative 38.66 degrees, which we're going to call, because we're going to put it between 0 and 360, 321.34 degrees. And now because I have my theta and I have my r, I can write this as r CIS 321.34 degrees. Or you can write it out the whole way, square root of 41 parenthesis cosine of 321.34 degrees plus I sine 321.34 degrees. Those two forms are equivalent. Oops, didn't mean to. Okay, all of that was lots of fun. And that's really the bulk of 8.2. However, I'm pretty sure the next problem shows up in your homework, so let's go over it. You have my word. I will not put it on your test, though. You're welcome. So this is something you see in higher levels of math, a fractal. So at its basic level, a fractal is a unique, enchanting geometric figure with endless self-similarity property. The fractal image repeats itself infinitely with ever-decreasing dimensions. It will look smaller and smaller, even though it is completely similar to itself. So if you zoom way in here, the big one's in the middle, and then you can see all the little pieces. All these little pieces over here that keep getting smaller and smaller, and then here's the big piece again with the pieces outside of it, and if you could zoom in it was clear, there's another big one right here with little pieces around it. It's just a really cool math thing. Fractals, we use them. So the Julia set is a very special fractal. So the Julia set, which is shown down below in this picture. Hang on, I wrote over part of this. So to determine if something's in the Julia set, we use that z equals a plus bi is in the Julia set, but the absolute value, the magnitude, must never exceed 2. If that happens, then the complex number z, this thing right here, would not be in the Julia set. So as long as its absolute value, its magnitude, is less than 2, it is in the Julia set. So we're going to use this pattern right here, and I'm going to number them. So this is the first number, this is the second number, this is the third number, and then so on. So we're going to use what I just numbered to determine below if what is given, the complex number z, is in the Julia set. So I'm going to number over here to the side. 1, 2, and then 3. And hopefully I can fit the math in here. We're going to have to do this twice. Okay, so for the first one, it said that the first pattern was called z squared minus 1. So we're going to take this thing z right here. So we're going to do 0 plus 0i squared plus 1, which is going to be 0 plus 0i times 0 plus 0i, because that's what it means to be squared, plus 1. Well, 0 times anything is 0. Oh, not plus 1. It's minus 1, sorry. Minus 1. 0 times anything is 0. So if I follow this out, I'm just going to get 0 minus 1, which is just negative 1. That thing's magnitude, length, absolute value is 1. So that number's in the Julia set. So the first one's okay. The next number in the Julia set is called z squared minus 1 squared, and then minus 1, which is right here. This thing right here is where I'm getting that from. So when I go down here, first I'm going to do this thing right here is z squared minus 1. It's this piece right here. That's this right here. So I can do negative 1. And then this square right here is this square right here. And then I have minus 1 at the end. So negative 1 squared is 1, minus 1, which equals 0. And the absolute value, magnitude, length of 0 is 0. That's in the Julia set. And let's try the next one, because we have to keep going until we find the pattern that repeats itself. So let's try the next one. The next one from that pattern listed above was quantity, parenthesis, z squared minus 1 squared minus 1 squared. So what I'm doing is taking this quantity from up here, which is right here, and then I'm just squaring it. And then I need to, after I square it, subtract 1 again. So if I go back up here, z squared minus 1 squared minus 1, the thing I highlighted in green, is 0. So I take my 0, and then I have to subtract 1 with it. That makes negative 1. Well, the absolute value of negative 1 is 1, and I've repeated. I've gone from -1 to 0 back to -1 again. So this number z, yes, it is in the Julia set. It repeated itself, so I don't have to keep going anymore. I found the pattern. It's going to go -1, 0, -1, 0, -1, 0, and all of those numbers have an absolute value that is less than 2. Let's try B. So I'm going to write the thing over here to the side. So number 1 was z squared minus 1. So here's my z. So I'm going to get 1 plus 1i squared minus 1. 1 plus 1i times 1 plus 1i minus 1. When you FOIL this out, you should get 1 plus 2i plus I squared minus 1. I squared is the same thing as -1, which means that 1 and minus 1 are going to cancel off with each other, leaving me with my 2 equals 2i and then minus 1. So if I go find the magnitude of this, like the radius, the r, let me write this in the other. This is going to be -1 plus 2i. Here's my x, here's my y. And so r equals the square root of x squared plus y squared. R equals the square root of -1 squared plus 2 squared. That's going to be the square root of 1 plus 4, which is the square root of 5. And the square root of 5 is bigger than 2, so automatically, no, this is not in the Julia set because the magnitude of this z, the r, is the square root of 5, and square root of 5 is greater than 2.